Swayam Prabha. Digital India. Educated India.
Welcome to the class. Till time we had seen that steam power cycle, which is Rankine cycle for us, has many components, and then how to evaluate their performance and how to work out with different interactions like work and heat in the different components. What are the corresponding methods to evaluate, what are the optimality conditions, and what are the different performance parameters. These were discussed in earlier classes. Now in this class we are going to discuss about steam power cycles and their examples. So let us see first example. This example says that a steam power plant with inlet steam to the high pressure turbine at 90 bar and 500 degrees Celsius and condensation at 40 degrees Celsius produces 500 megawatt of energy. So we are given with 90 bar pressure and 500 degrees Celsius as the temperature of the steam at the high pressure turbine inlet. It has one stage of reheat which is taking place at 20% of boiler pressure, which rises the temperature back to 500 degrees Celsius. So we have one reheat, single stage reheat, and then after reheat temperature is 500 degrees Celsius. One closed feed water heater with drains cascade backward. So we have one feed water heater also which is draining cascade backward towards the condenser, receives bleed from steam at reheat pressure. So reheat pressure we know it is 20% of boiler pressure, and the remaining steam is reheated and then expanded in the low pressure turbine. HP and LP turbines have isentropic efficiencies 92% and 90% respectively. We have isentropic efficiency of pump which is 75%, and then we have to find out mass flow rate of steam at the inlet, cycle efficiency and cycle work ratio. So for us this is a typical TS diagram for this example. So in this example what we know? We know that P3, P2 is equal to P3 is equal to P4 is equal to 90 bar. Similarly T4 is equal to T6 is equal to 500 degree Celsius. Then we know that P8 is equal to P5 is equal to 0.2 of P3, and it is, that is why 18 bar. We are also given that turbine efficiency is, if it is HP, if it is HP turbine, then efficiency is 92%, and if it is LP turbine, if it is LP turbine, then efficiency is 90% and efficiency of pump is 0.75. So these are the things which are given to us. We are also told that P1 is equal to P7 is equal to P9 is equal to the pressure corresponding to 40 degrees Celsius. So practically we are given with T1 is equal to T9 is equal to T7 is equal to 40 degree Celsius. So we know the P1 is equal to P9 is equal to P7, and that is equal to the pressure corresponding to 40 degree Celsius saturation temperature. We are also told that TTD is equal to minus 1.6 degree Celsius. So this implies that T3 is equal to T8 plus 1.6 as per the definition of TTD. So we know TTD is equal to saturation temperature minus the exit temperature of feed water. So saturation temperature minus 1.6. So we can know that T8 plus 1.6 is now T3. E is now T3. So knowing this, we can start evaluating. So we know P1, which is 40 degrees Celsius saturation condition. So we can go to the steam table, go to the saturation temperature part in the steam table, find out 40 degree Celsius, and then corresponding saturation liquid enthalpy is H1, and that is 167.57. This is known to us. Then we know that actual pump work is to be evaluated, but before that we will evaluate the ideal. Dash means ideal pump work, and for ideal pump work we can use V1 into delta P, and delta P is the pressure difference between this pressure corresponding to 40 degrees Celsius and 90 bar. This pressure difference is delta P. V1 is the specific volume at this state. So this will give us pump work in ideal case, but we know that pump efficiency is given 75%. So that is not the correct work which is actually requiring in pump. So knowing this, we can find out H2 dash. Basically H2 dash is found out from the fact that we know H2 dash minus H1 is equal to delta P dash, and delta P dash is evaluated using this formula. H1 is known, then we can find out H2 dash. Then we know that actual pump work is ideal pump work divided by efficiency of pump. So but actual pump work is H2 minus H1. So here ideal pump work divided by 0.7 can be evaluated using this H2 minus H1, within which H1 is known. So we can find out H2, and so H2 is 179.61. Then we know that S6, now we are directly coming to the low pressure turbine. This is low pressure turbine, this is high pressure turbine. So we know entropy at 6 is equal to entropy at 7 dash, but entropy at 7 dash is equal to SF plus X7 dash into SFG. Basically SF is equal to S1, and this is, if we go to liquid saturation entropy corresponding to 40 degrees Celsius saturation temperature, then we can know SF. SFG is latent entropy change, and that is also given in the steam table. S6 is, we will go to the supersaturated part or superheated part of the steam table, we will go to the 90 bar pressure and 500 degrees Celsius temperature, and then from that we will pick up the entropy. So these things are known to us. So knowing these things, we can evaluate X7 dash, and X7 dash turns out to be 0.899, so which can be taken as 0.9. So knowing X7 dash, we can find out H7 dash, where H7 dash is practically is equal to HF plus X7 dash into HFG, where this HF is actually equal to H1 and HFG is latent change in enthalpy or latent heat. So we know now evaluated the H7 dash. But again we can use efficiency of turbine, which is low pressure turbine efficiency is 90%, into the ideal turbine work is equal to actual turbine work. So here we now know H7 dash, we know H6. H6 is known to us, it is corresponding to 18 bar 500 degrees Celsius. In the superheated part of the steam table we know H6. So H7 dash is known to us from previous step. So similarly we know H6 here as well, and thus these things can be used to find out H7, which is this point. So knowing H7, we can find out as well, if required, the X7 from the point that H7 is equal to H1 plus X7 into HFG, where HFG is known to us from the steam table, where we had used it over here, and then we know H1 we had also used it over here. H7 has been calculated, then we can find out X7 if required. But before that, we can find out high pressure turbine. In case of high pressure turbine, this is actual work is equal to efficiency of high pressure turbine into ideal work. So here ideal work is needing the enthalpy at H5 dash. For that, we can go to the steam table superheated part, we can go to 500 degrees Celsius and 90 bar, and then find out the H4. So H4 is known, and then we can go to the same point and find out S4, but S4 is equal to S5 dash. So we know S4 is equal to S5 dash. So S5 dash is the entropy corresponding to 18 bar pressure, and then we can find out, go to 18 bar part of the steam table, find out the entropy at that state, which will correspond to entropy of S4. Knowing this, that location will have certain enthalpy of the steam, which may be wet or which may be dry. We will pick up that entropy enthalpy, and that enthalpy is H5 dash. So H5 dash is known to us, H4 is known to us, H5 dash is known to us. From that we can find out H5. So similarly, H8 is the saturation liquid enthalpy at 18 bar pressure. So example 1 is continued. Now 18 bar pressure has saturation temperature which is 207.15 degrees Celsius. We had also seen that TTD is given to us. So this is saturation enthalpy, saturation temperature plus TTD is the temperature at T3. This will be useful to us to find out enthalpy at 3. But this enthalpy is the subcooled enthalpy corresponding to 90 bar liquid water. This enthalpy would be available again in some steam tables. Otherwise, we could also approximate it to the saturation temperature as 208.75 degrees Celsius, and that saturation liquid enthalpy can also be approximately taken equal to same. Then, knowing this, we can find out M, which is mass given for the bleeding, and then that mass is basically can be found out from the energy equation. What we are writing, that 1 kg of steam is rising its enthalpy from 2 to 3 at the cost that m kg of mass of blade is losing its enthalpy from 5 to 8, from 5 to 8. So we know now H3, we know H2, we know H5, and we know H8 from last steps, and then we can find out M, which is 0.336 kg. This can be helpful for us to find out turbine work, and turbine work is H4 minus H5, H4 minus H5, which is high pressure turbine work, HP turbine, and then we have 1 minus M into H6 minus H7. This is low pressure turbine. So these two turbine works will be added to find out turbine work. Then net work is turbine work minus pump work. We had already found out actual pump work. So this will be the net turbine net work of the cycle. But we were told that this net work is Ws into W net, and this is equal to 500 megawatt. So this will be helpful to us to find out Ws, and this Ws is 454 kg per second. Now we can find out Q1. Q1 is amount of heat supplied. So amount of heat supplied is H4 minus H3, H4 minus H3. This is the heat given in the boiler. So, this is heat given in the boiler, and then this is the heat which is given in reheater, H6 minus H5, H6 minus H5, and this is Q1. So, cycle efficiency is W net upon Q1 or Q in. So, we found out cycle efficiency, which is 38.58%. Then work ratio is W net upon WT. W net is known to us from earlier step, and WT is turbine work, that is also known from earlier step. Then we know work ratio. So, this is how we would have solved this example, and we would have estimated all the necessary parameters. Now, let us go to the next example. Next example says that there is a textile factory which requires 10 ton of steam per hour for the process heating. So, it is a process heating, industrial heater is used to heat some object or some matter, where 10 ton of steam is considered as the heat source per hour, and then that heating is taking place at 3 bar saturated condition. So, steam for the process heating is supplied at saturated condition, that is the given fact for us, and then the work done is 1000 kilowatt by the cycle. We are obviously using a back pressure turbine, and then that turbine has 70% thermal efficiency. We are supposed to find out condition of the steam required at the inlet of the turbine. We are given that neglect the pump work. So, given this fact, we can draw the TS diagram, and this TS diagram will be like this, where we are said that pump work is neglected. So, we have not drawn any pump here. Then pump is here itself. State 1 is complete pumping. 2 point is purposely shown so as to find out the saturated state corresponding to P1. So, we are told that mass flow rate of steam is given, and that is 10 ton per hour, and then we are given that P2 is equal to P3 is equal to found out. We are supposed to find out this, but we are given that P1 is equal to P4 is equal to 3 bar. We are also told that turbine efficiency is 0.7. We are also told that H3 minus H4 into mass flow rate of steam is 1000 kilowatt. So, this is given fact for us. So, we do not know what is the temperature, and also we should know T3. So, we do not know where is this state. So, logic is that we do not know this state, but we know that this turbine is 70% efficient, and supply like X4 is equal to 1. Supply is saturated. So, this point is saturated, a real point is saturated. So, from the real point we will find out ideal point, which is X4 dash. From the ideal point we can find out entropy at ideal point, and then we can see that the same entropy is at X3, and then we can find out. This is the logic of solving this example. So, let us see how we are going to solve this example. So, we know that H4 is a saturation condition, and that is at 3 bar. So, at 3 bar we can find out saturated steam enthalpy, and that is H4, and then we know that as what we are telling that turbine work is 1000 kilowatt, and then that is equal to mass flow rate of steam into change in enthalpy of the turbine. So, we know H4, we know turbine work, and we are also given with the steam, which is 10 ton per hour. So, knowing this we can find out H3 minus H4, but within that H4 is known to us. So, this will be helpful to find out H3. So, H3 is known to us. Then H3 is known to us, but then we can use the formula for turbine work. So, this is the ideal turbine work, and this is the actual turbine work divided by the efficiency. So, actual turbine work is known, efficiency is known, H3 is known, then we can find out H4 dash. and this H4 dash belongs to 3 bar pressure. So, from this we can say that H4 dash is equal to HF plus X4 dash into HFG. So, we can go to 3 bar pressure in the steam table, we can find out liquid saturation enthalpy, we can find out latent enthalpy, we know H4 dash from previous step, then we can find out X4 dash in the point which is ideal turbine exit. Knowing X4 dash, obviously we can find out S4 dash, which is entropy at 4, and this is again same as SF plus X4 dash into SFG. This is liquid saturation entropy, this is latent entropy change, and X4 dash. Now S4 dash is known, but S4 dash is equal to S3. So, we know that from the Mollier chart, we know Mollier chart is the diagram where y axis is enthalpy, x axis is entropy. So, we know now enthalpy at 3, enthalpy at 3 is known to us, we know entropy at 3. So, knowing entropy and enthalpy, we can find out the basically pressure and temperature at state 3 as well. If we are not following Mollier chart, we can go to the steam table, we can go to the particular entropy and then find out for this entropy when we would have enthalpy which is H3, and then we can take those pressures and temperatures. This point logically at this moment is lying into the superheated part of the steam table. Now, let us go to the next example. Next example says that there is a cogeneration plant where power load is 5.6 megawatt and the heat load is 1.163 megawatt. So, this is a cogeneration plant, means it is having two outputs or two objectives, one is to generate electricity and one is for industrial heating purpose. So, both are given to us. So, net work is given to us as 5.6 megawatt and heating load is also given as 1.163 megawatt. Steam is generated at 40 bar and 500 degree Celsius and is expanded isentropically through a turbine to condenser at 0.06 bar. The heating load is supplied by extracting steam from the turbine at 2 bar condition. So, the heating load is given at 2 bar condition, and then the rest of the steam condenses, or the steam taken for the industrial heating condenses in the process heater to the saturation liquid state at 2 bar and then pumped back to the boiler pressure. Basically, it is a forward cascading type regeneration, except for the fact that this is not used for feed water heating. Then we are expected to compute steam generation capacity of the boiler in tons per hour, heat input in the boiler, and then fuel burning rate in the boiler in tons per hour. We are given that the calorific value of fuel is 25 megajoule per kg of fuel and boiler efficiency is 88%. So, not all the fuel burnt is going to give the enthalpy rise for the steam, only 88% of the boiler, only 88% of the energy liberated from the process of combustion or fuel burning will be used to rise the enthalpy of the steam. And then we are supposed to find out heat rejected in the condenser if the change in temperature of the cooling water is 6 degree Celsius. So, let us plot the TS diagram. As per this TS diagram, what are the things which are given to us? We are given that P3 is equal to P2 is equal to P4 is equal to 40 bar and T3 is equal to 500 degree Celsius. We are also said that the process heating is taking place at 2 bar. So, we have P5 is equal to 2 bar and then this is also equal to P7. We are also told that combustion efficiency is 88%, but P1 is equal to P6 is equal to 0.06 bar. These are the given things with us, but we are told that net work is equal to WT minus WP, and that is equal to 5.6 megawatt, but we are told that pump work can be neglected. So, turbine work is 5.6 megawatt, and heating load in the process heating, which is H5 minus H7 into W, is equal to 1.163 megawatt. This is the given fact for us. So, knowing this, we can proceed for the example. So, we can go directly to the steam table at 40 bar and 500 degrees Celsius and find out H4. Then at the same state we can get the entropy, but this entropy is same as S5 and S6. We can use this entropy to find out the condition at 2 bar for the state 5. So, what is the enthalpy at 5? We will go to the 2 bar state, and then we will find out when this entropy will be equal to S4. From that we can get the H5. Initially it turns out that X5 is also equal to 1. So, it is a liquid, it is a vapor saturated state. So, we know H5 is equal to Hg is equal to 2706.7 kilojoule per kg. This would be giving us H5 minus H7 is equal to HFG, that is 2201.9 kilojoule per kg. This is taken from 2 bar, which is the latent heat. So, as what we are given, W into H5 minus H4 is equal to heat load. So, we can find out W, which is the steam required for the process heating. Then we can find out S4 is equal to SF plus X6 into SFG, and this SF is corresponding to 0.06 bar, SFG is also at 0.06 bar, S4 is known to us corresponding to 40 bar and 500 degrees Celsius. So, we can find out X6, and that is 0.84. We can use this to find out H6, since H6 is equal to H1 plus X6 into HFG, and this H1 is at 0.06 bar liquid saturation enthalpy, H5 is 0.06 bar the change in entropy for the phase conversion. Knowing this, we find out H6. So, turbine work is equal to the total amount of steam getting expanded and losing its enthalpy from 4 to 5 before passing Ws amount of steam for W amount of steam for process heating. So, W minus Ws amount of steam is getting expanded from H5 to H6 enthalpy drop. So, what we know this is equal to 5.6 megawatt. So, here H5 is known, H6 is known, H4 is known, H5 is known, Ws is known, then only we have to find out W, and this turns out to be 16.73 tons per hour. We obviously would be neglecting pump work, but the pump work to be neglected is the pump which is a condenser pump, but this pump is the pump which is pumping off the small amount of steam from the process heating pressure to the boiler pressure. We know H7 is the liquid saturation enthalpy at state 7, and then plus pump work, and pump work is V7 into delta P, where this delta P is pressure 40 bar minus 2 bar. Then we can get H3. We could as well, if at all, consider pump work. Here we can consider it as V1 into delta P, where delta P is 0.06 bar and 40 bar pressure difference. So, we know now H3 and H2 both. So heat added is split like this, where W minus Ws steam is rising its enthalpy from 2 to 4. 2 to 4 is the enthalpy rise for steam, which is Ws minus W. But small amount of blade steam for process heating will rise its enthalpy from 3 to 4. From 3 to 4. So this is what the total amount of heat given, and then this total amount of heat is 15.111 megawatt. But efficiency of boiler is given as 88%, where efficiency of boiler can be said as amount of heat given divided by amount of heat liberated in combustion. So this is calorific value into mass of fuel. So Q1 is evaluated from earlier step, calorific value is given, then we can find out Wf, which is 2.473 tons per hour. Then Q2 is amount of heat rejected, is Ws minus W into enthalpy drop in the condenser H6 minus H1, and amount of heat rejected is 8.37367 megawatt. Then but amount of heat rejected is equal to mass flow rate of water and into specific heat of water into change in temperature of liquid water used for cooling purpose. So this side, right hand side, is for the cooling water, which is used in the condenser to take the heat from the steam and to make it liquid saturated, and this is the amount heat which we are finding out. Now using this we can find out the asked quantity, which is the coolant flow rate. So amount of coolant which is flowing into the condenser to take the heat, that can be found out, since this delta T is given as 6 degree Celsius. So this is how we can work out and solve the example. So these are some examples which we have solved for the conventional Rankine cycle and Rankine cycle with attachments, some like reheater or regeneration, or also the examples of back pressure turbine. We will solve some more examples in the next class. Thank you.